All right, so this is a review for the final exam, also known as Test 5. And basically, we've kind of gone over this before, but the breakdown of the test is Section 1 is multiple choice. Each of the multiple choice questions are worth 3 points each. And this section is very cumulative. So it's going to be different multiple choice questions from the whole semester. So best way to study for this section is to go through all the concepts that are on the first page of all the test review sheets that I've handed out all semester, which are also available in Blackboard, like if you lost yours. So I'd say that's the best way to study for it. There is one problem that asks you to do a calculation in there, but it's small. Like I wouldn't focus on the calculations. There's nothing like the last exam where there was all those really horrible, big, yucky calculations involved in those 4-step problems and everything. So, it's pretty, you know, there's stuff clear from the beginning of the semester. There's stuff from the middle. There's stuff that kind of integrates things from middle and end, the multiple choice. So then the next section is problems. The problems are going to come from the new material. So the 3 review questions that were on the test review sheet, those are a really good example of what you can expect to see on the test itself. And then of course the problems that we go through today, those are all going to be very similar to the types of problems that you're going to see in the problem section. And there's like 20, I can't remember how many there are now. I think there's about 20 problems, but there's 20 questions, but there's really only like 4 or 5 actual problems. There's just multiple questions that go with each one. So one question would be, hey, what's the hypotheses? And another question is going to be, how many degrees of freedom do you have? And the next one is going to be, you know, do you meet the requirements? Or, you know, what's your test statistic? So there's multiple questions, each worth 3 points that go with each problem. And a lot of it does involve just looking at mini-tab output. So this test really does go pretty quickly, relatively speaking, to the last one. And then the last section is matching. There's 6 matching problems. There are different scenarios. And you are just going to choose the right statistical analysis for whatever scenario is there. So now we have 8 different things that we're choosing from, the 5 from last time, plus chi-square, ANOVA, and regression. So really, all the stuff that we talked about in preparation for the last exam is how you're going to kind of figure out what the right statistical analysis is going to be for a particular scenario. So looking at the problem and first deciding, do I have, you know, categorical or quantitative? And then once you decide that, then you kind of ask, do I have 1 group, 2 group? And then we can add on 3 or more groups, because that's kind of the last column in that flow chart that I gave you guys. And that kind of really covers it, except for regression. Regression is a little bit different. It's not even on the flow charts that I gave you. And the key thing to look for in a regression problem is, most of the time when we're doing regression, our goal is to make predictions. So we're going, if it says, hey, we want to be able to use height to predict weight, well, then that would be an indication that you're dealing with regression. The other thing with regression is that both of the variables in regression are quantitative. So in all the other scenarios, you don't have two quantitative things that you're measuring on the same individual. So the fact that you have 2 quantitative variables sets that one apart as well. So when you add up all those, because like everything, it's easiest to make everything worth 3 points on the exam, it actually adds up to 102 possible points, but I'm only scoring it out of 100, so there are potential that you could get 2 extra credit points if you wanted to. So, so you might want to, I can hear somebody, you might want to just mute yourself if you're not, I can't see everybody at the same time, so I can't tell who's the noisy one. But if you're not speaking, you might want to mute yourself just so that none of your background noise comes over the speaker too. All right, so first let's talk about chi-square. So here's the example. A large randomized trial was conducted to assess the efficacy of Chantix for smoking cessation compared with bupropion and a placebo. Chantix is different from most other quit smoking products in that it targets nicotine receptors in the brain attaches to them and blocks nicotine from reaching them, whereas bupropion is an antidepressant often used to help people stop smoking. Generally, healthy smokers who smoked at least 10 cigarettes per day were assigned at random to take Chantix, bupropion, or a placebo. The study was double-blind, with the response measure being continuous absence from smoking for weeks 9 to 12 of the study. So here's what the data looked like for this one. And we want to know if there is a difference in the drugs. So what would be the overall hypothesis test, what would be the hypotheses for the overall test? So this one, we're dealing with two categorical variables, the treatment and whether or not they were able to stop smoking. So because we have two categorical variables, then that would lead us to doing a chi-square. Another way we can know it's a chi-square is because we could look at it as comparing three different proportions here. So let me turn on my pen here. So really what this looks like is we're comparing P1, P2, and P3. That's a 3. P1 could be the proportion of Chantix users that stop smoking. So P1 proportion of Chantix who stop smoking. P2 would be the proportion of bupropion users that stop smoking. And P3 could be the proportion of the placebo users who would stop smoking. So if we think of this as three proportions that we're comparing, then one way we could write the hypotheses are null hypothesis P1 equals P2 equals P3. And alternative hypothesis is that at least one P is different. All right, so one thing to note about writing the hypotheses this way is the null hypothesis is that they're all equal, but the alternative is not that they're all not equal. So it would not be right to say P1 not equal P2 not equal P3. That would be incorrect. So because our alternative is just that at least one has to be different. They don't all have to be different. They might all be different, but they don't have to be in order for, that's not what our alternative is. It just says at least one of them, possibly more of them, are going to be different from the others. So we actually have two ways that we can write the hypotheses for a chi-square test. This first way that I just talked about just now, this works a lot of the time, but it makes sense when, if you could actually like write down what P1, P2, and P3 or P4, however many there are, and it makes sense in the context of the problem, then this is going to be a good way to write the hypotheses. But if you're kind of looking at your table and you're like, I have no idea what to call P1 and P2 and P3, then the second way is going to be a better option for writing your hypotheses. So in the second method for writing the hypotheses, what we do is we look at the row and column variables. So we look at the columns here. This is basically our treatment. And if we look at the rows, this is whether or not they quit smoking. That's kind of like a, did they stop smoking, yes or no kind of thing. So if we think about it that way, then we're really just looking to see if there's a relationship between these two categorical variables. So null hypothesis would be no relationship. And for some reason, my pen's just drawing lines wherever it feels like drawing lines today, so it looks really scratchy on here, and I apologize for that. So no relationship between treatment and stopping smoking. Versus the alternative that there is a relationship. So there is a relationship between treatment and stopping smoking. All right, so both of these will work in this case. The second way, the no relationship versus there is a relationship, that one is going to work all the time, whereas the other one sometimes is harder to come up with when it works. But either one is going to be good in this instance here. So something else to note is that when we talk about regression and we're looking at relationships between two quantitative variables, then one way of writing the hypotheses is the same as the second way, only we're talking quantitative variables. So it's still, though, null hypothesis, no relationship, and alternative hypothesis, there is a relationship. And if it helps you remember like which is which, like think about when we write null hypothesis, we're usually saying like something equals something, or something's not different. So no difference is our null hypothesis, and there is a difference is the alternative hypothesis. Okay, so in order to do this test, then we need to first find the expected count for each cell. So expected count, we find expected count by taking the row total times the column total and dividing by n, our overall table total. So in my chart here, n is going to be this 1025 over here, and then the totals we just get from the row and column totals columns. So starting with this first cell right here, the Chantix users that were able to stop smoking, then my expected count is going to be the row total for that, which is 313, times the column total for that one, which is 352. So I have 313 times 352 divided by 1025, which is n, my overall table total. So if I do that calculation, just getting out my calculator here, I have 313 times 352 divided by 1025, and I get 107.49. So that equals 107.49. So if I'm writing that up here in my table, I'll put 107.49. All right, so then I could find the expected count for the next cell. So same thing, if I'm looking at bupropion with not smoking, then my row total is 313, and my column total is 329. So I'm going to have 313 times 329 divided by 1025. So that gives me 313 times 329 divided by 1025. So I get 100.47. So that'd be the expected count for that cell. So I would keep doing this for all the 6 main cells that actually contain observed counts in them for this table. So, so this is a 2x3 table, so I'd have six expected counts that I would need to calculate. So here on the next screen, I've got all the expected counts in there. Now if I'm ready to calculate the test statistic, the name of it is chi-square, of course. And we calculate chi-square by taking the sum of the observed counts minus the expected count squared divided by the expected count. So I am going to have this calculation that I'm going to do for all 6 of these cells here. So starting with the very first cell, just write it all out. Then I'm going to have the observed count, which was 155, minus the expected count, which is 107.49. Square that and divide by 107.49. So that's it for the first cell. Plus, then I move on to the second cell. I'm going to have 97 minus 100.47. That quantity squared divided by 100.47. Plus, go to the next one. I've got 61 minus 105.05 squared divided by 105.05. Plus, now I'm on to the second row. I've got 197 minus 244, that was a 4, 244.51 squared divided by 244.51 plus, I'm going to come down here to the next line, I ran out of room, plus 232 minus 228.53 squared divided by 228.53 plus, I think we finally made it to the last one, 283 minus 238.95 squared divided by 238.95. So got that all written out now. Now it's time to go ahead and start working on the individual calculations there. And I do it separately for each of these because those numbers, those contributions to the chi-square are going to become important when we delve into the deeper analysis if this turns out to be significant. So I'm going to start with that first cell there. So I have 155 minus 107.49, which is 47.51. I square that, which gives me a big number, 2,257.2, and then I divide that by 107.49. So I get 20.999 for that one. 20.999. Plus, now I do the next one. So I have 97 minus 100.47. Square that and divide by 100.47, which I get 0.1198. Plus, going on to the next one, I've got 61 minus 105.05. Square that and divide by 105.05. It's 18.47. So there is one of these problems on the exam where you are going to have to work out this stuff. But the good news is I picked like the absolute smallest possible two-way table that I could come up with for you to do it on. So it shouldn't be too tedious on the exam. Okay, so now I'm on to the next one, which is the start of my second row there. So I have 197 minus 244.51. Square that and divide by 244.51, which is 9.231. Plus, next one is 232 minus 228.53, square that and divide by 228.53, which gives me 0.0527 plus the last one here, so I have 283 minus 238.95, square that and divide by 238.95. And I get 8.12. 121, yes. All right, now I have all the pieces, so I'm just going to add all of those together to get my actual chi-square statistic. So I ended up with 56.994, or 995 actually. Either way, pretty close to 57. So this is a pretty big number. So next step from calculating our test statistic here is going to be to find our p-value. And this is a chi-square test statistic. So we use the chi-square distribution table to help us find our p-value. And in order to use that table, we need to know how many degrees of freedom we have. So degrees of freedom for a chi-square are equal to the number of rows minus 1 times the number of columns minus 1. That was a minus. So in this case, we have 2 rows. So we're going to have 2 minus, something about the bottom of the screen that my pen doesn't like. 2 minus 1 times the number of columns, which is 3 minus 1. Remember, when you're counting rows and columns, you do not include the totals in that. So 2 minus 1 is 1, 3 minus 1 is 2, so I end up with 2 degrees of freedom. So heading over to table D, I would look along the row for 2 degrees of freedom, and I'm looking to see where 56.995 would fall. And if you look clear down here, you can see that it's way, way, way off the table this way. And looking at this trend of p-values on my table, that just means that my p-value is going to be super duper itty bitty, like practically 0. So p-value is approximately 0. Just put that. All right, so if my p-value is close to 0, I'm trying to remember if I put another, nope, I didn't. I thought I had another slide in there. Then p is low, HO must go, so we're going to reject the null hypothesis, which was that all the proportions were equal, and we're going to conclude that at least one proportion is different. Or if we're using the second set of hypotheses, we'd conclude that there is a relationship between the treatment that was used and whether or not people were able to stop smoking. So now we can kind of take this to the next step and figure out where those differences are. So switching up my colors here. So what I do for this one is I look back at all those contributions to the chi-square, and I'm looking for the biggest ones, and I'm going to kind of examine what's going on in those cells and see if that helps me figure out where all these differences are coming from. So really that corresponds to what's going on here with Chantix and what's going on with the placebo. So if we look at Chantix, it says in this first cell there was 155 people that were able to stop smoking. We would have expected only 107 if all the treatments were the same. So a lot more people were able to stop smoking than expected with Chantix. Looking at the placebo, we see the opposite. So we had 61 people who were able to stop smoking. We would have expected 105, so a lot fewer people who took the placebo were able to stop smoking. And then the bupropion was kind of in the middle. It was what we expected because we had all the same, pretty close to the same sample sizes. Then it's just saying, hey, Chantix is a lot better than what we expected. Placebo is a lot worse, so bupropion ends up being kind of in the middle. So what do we conclude from that? Well, it looks like Chantix is the best for getting people to stop smoking. It is significantly better than either bupropion or the placebo in helping people to stop smoking. But it looks like bupropion was also better than the placebo, or in other words, the placebo was worse than the bupropion for helping people to stop smoking. So when you're looking at your conclusion for chi-square, you should really do both. You should look at the p-value and say, okay, do I reject, fail to reject that? And then look at the details and say, okay, that means that, you know, we can tell from our table that Chantix was the best at getting people to stop smoking, placebo was the worst, or something like that. So on the exam, there's one problem where you're going to do the chi-square by hand, just like we just did just now in that problem. And then there's going to be another problem where you have, it's actually Minitab output that we're going to look at. So this output that is here for this problem is not from Minitab, it's from a different software program, but it's very similar, very close to the same thing. You're looking for the same kind of things on these outputs. So let's start with just looking at our hypotheses. So this problem says, a sample survey asked young adults aged 19 to 25, what do you think are the chances that you will have much more than a middle-class income at age 30? Based on the output, what can you conclude? So in this case, this is one of those cases where it's not really clear right off the bat, like what you would call P1 and P2 and P3. There seem to be a lot going on in this problem. It makes more sense to me to think of this problem as, oh, let's look at the relationship between gender and your perceived chances of being rich by age 30. So if I did that, then null hypothesis would be no relationship. No relationship between sex and perceived chances of being rich by age 30. And the alternative hypothesis is that there is a relationship between sex and perceived chance of being rich. So there is a relationship. And of course, when you're writing the hypotheses, make sure you're specific to the question. Don't just put no hypothesis, no relationship, alternative hypothesis, there is a relationship. Like, spell out what the variables are. So there is a relationship between sex and perceived chance of being rich. So here's our hypotheses, and when the computer does it, it's already got the test statistic right there for us. It's this chi-square down here, which is equal to 43.946, and it gives us the p-value here of less than 0.0001. So our p is really, really low, so HO would go, and we would reject the null hypothesis and conclude that there is a relationship between sex and perceived chances of being rich. I'm sorry, it looks like I crossed out being rich. I didn't really. Like I said, this computer pen, maybe it's time for me to buy a new tablet because I've been having lots of problems with it today. Okay, so we need to now look back at the table and try to figure out what is the relationship or what's going on here. So anytime you have a table that's outputted from any statistical package, including Minitab, they're going to give you a key somewhere that tells you what they're giving you in the table. So this key up here tells us that the top number is the observed count. The second number is the column percentage. So that's actually the, so since we're taking the percent of the column, it's actually the conditional distribution for female and male separately. And then we have our expected value and the contribution to the chi-square. So the cell chi-square number, that's what we're going to look at to kind of figure out where to examine what's going on with this data. And you can see that the largest ones are here. Both of these are 16 plus. And then we got some, not nearly as big as 16, but they're a little bit bigger on down there. So looking at these kind of groupings, we might be able to figure out what's happening here. So at the top one, this says some chance. You only thought you think you have some chance, so less than a 50-50 chance, in other words, of being rich by age 30. So for the females, there was 426 in this group, but we would have expected 349 if there was no difference between males and females. So there was a lot more females that were saying, you know, like not good chances of being rich than what we would have expected. And looking at the males, there was 286, we would have expected 362. So there were a lot fewer males that were saying that there was only some chance of being rich. Then down here, nearly certain, there was 486 females when we would have expected 531. So a lot fewer females were nearly certain about being rich, whereas the males, 597, as opposed to 551. There was a lot more males than what we would have expected. So just kind of looking in general at the pattern that's going on here and the differences between these numbers, it looks like that boys tend to be a little bit more optimistic about their chances of being rich by age 30 than girls. Girls seem to be a little bit more pessimistic about their chances of being rich by age 30. So we can mention that in our conclusion when we say, hey, yep, we're rejecting, there is a relationship, and it looks like men are more likely than women to think that they are going to be rich by age 30. All right, that kind of sums it up for chi-square. Does anybody have any questions about chi-square before we continue? Awesome. All right, so let's look at regression. We're interested in seeing if there's a relationship between a person's height and their arm span. Data was collected on 29 college students, and here's a scatter plot of the results. So we're looking for three basic things on our scatter plot. We are looking for form, direction, and strength. So form, what's the overall pattern? And we're most interested in finding out if there's going to be some kind of linear pattern. So especially now that we're all looking at a computer screen, like if you kind of hold your pen up and close one eye and you know, move the pen in and out in front of that plot, if you can cover up most of the points with that straight pen, then it's going to be a linear relationship. This is that, you know, fat hot dog test that we talked about, only if you don't have a hot dog handy, your pen works just as well. So in this case, like if I do that, it definitely does look like a linear relationship using that method. So we have a linear relationship. The second thing is direction. We have positive or negative. If it's positive, if as arm span increased, height also increased. And that's what we see here. So if it goes from bottom left to upper right, that kind of linear form, then that's going to indicate that we have a positive relationship. And negative is going to be the opposite. It's going to go from top left to bottom right. And then finally, the strength. Well, you know, how close did you have to move that pen to your face before everything started to kind of fall behind the pen? You know, how closely do the points cluster around a line? Well, that's going to tell you how strong it is. So in this case, I'd say, hey, you know, it's decent. It's like, you know, moderately strong. It's not super tight, but it's very clearly a linear pattern, which would indicate at least, you know, a good moderate to strong relationship. All right, so here's some Minitab output from regression analysis for height versus arm span. So first question says, what are the estimates for the model parameters? So remember, parameters are population values. So in this case, because we're looking at regression, then our model parameters are going to be alpha and beta, where alpha would be the population intercept, and beta is going to be the population slope. So to estimate alpha and beta, then we use A and B from our sample. So over here on our output, we can get those from our regression equation. That's one place. So the A, or the estimate for intercept, is 20.5, and B, the estimate for slope, is going to be 0.703. So we don't care that much about the intercept, other than the fact that we need it to make our model function. But we can always interpret that number for slope, so we find it interesting. So this tells us that for every 1 inch increase in arm span, we would expect a person's height to increase by 0.7-ish inches. So to answer the question, we have A equal to 20.5 and B equal to 0.703. So next question says, what % of the variation in height can be explained by arm span? So this was the quote-unquote trick question back from the second test. Not really a trick question, but it's tricky because it's giving you the definition of what R squared is, rather than just saying, hey, what's R squared? So remember, R squared tells you the % of the variation in the response that can be explained by your model. So we can find R squared right here on our output. Excuse me. So R squared equals 64%. So in other words, 64% of the variation in height can be explained by arm span. And then lastly, this one says, what's the value of correlation between height and arm span? So to get correlation just from the information that's right here on our output, then we're going to have to use R squared. And remember that R is just the square root of R squared. And the key to finding R this way is to remember that when we use R squared in calculations, it always has to be changed to a decimal. So that 64% is going to become 0.64 as a decimal. When I take that square root, then I get 0.80. Now, the other thing about taking square roots is that it can be either positive or negative. So to figure that out just by what we have here is we look at the sign on our slope. So whatever sign is slope has, same sign on R. So positive in this case. Also, we can look at our scatter plot and we can see that it was a positive relationship. So that's also going to tell us that we have a positive value for R. All right, next question. What is the test statistic for testing null hypothesis, no linear relationship between height and arm span, versus the alternative that there is a linear relationship between height and arm span? So this question is answered by a t statistic. T is equal to b divided by the standard error of b. So in our output over here, we have our coefficients table, and we're always going to ignore the first line because that corresponds to the intercept, and the one we want to focus on is the second line because that corresponds to the slope. So remember in Minitab speak, then B is the coef, and SEB is the SE coef. So for this particular case, then our coefficient is 0.7033, and we're going to divide that by the SE coef, which is 0.1015. So if I do that calculation, you have 0.7033, 0.1015, so I'm dividing those, and I get 6.93. So T equals 6.93. So that's the test statistic for that particular set of hypotheses. Now the second question says, what's the test statistic for testing beta equals 0 versus beta greater than 0? And remember that this test statistic is the amazing 3-for-1 special. So same test statistic. So T equals 6.93. And notice in my output over here, somehow my whiteout bottle even made it to the computer screen and erased the values of T. When you do this in Minitab, it'll actually tell you the test statistic. But on the exam, it's possible that it's going to be missing, so you're going to have to calculate it by hand, which isn't that hard. We just did it. But just be aware that you might have to calculate that. So, and we did say this is a 3-for-1 special, so this is one way of writing the hypotheses. This is the second way of writing the hypotheses, and the third way involves R. So null hypothesis R equals 0 versus the alternative that R is, since we use greater than there, I'll use greater than here, greater than 0. So three ways of writing the hypotheses. They're all answered by using the same test statistic and also the same p-value. So we just calculated that test statistic. Now we want to know how many degrees of freedom does that test statistic have. I'll write it in here, my test statistic, 6.93. So degrees of freedom for regression are equal to n minus 2. So n, if you remember, oops, there it is. On this page, we had 29 college students, so 29 is my n. So 29 minus 2 gives me 27 degrees of freedom. And finally, what's the p-value for this test? Well, this is a t-test statistic, which means that we're going to use table C, our t-distribution table, to help us find that test statistic. So here's my table. I'm looking at the line for 27 degrees of freedom, and I want to see where 6.93 would fall, and is somewhere way out here, falling off the charts, which means that my p-value then is really small, practically 0, less than 0.0005. Any of those will work. So p-value less than 0.0005, or pretty close to 0. So if my p is low, HO must go. And remember, this is testing all 3 of those tests. So really all 3 of those tests would go. Where are they? Oops. Down one more. Okay, there we go. So we'd reject all of these null hypotheses, and we would conclude that indeed there is a relationship between height and arm span. The slope is positive and the correlation is positive. So our next question would be then, well, what is the slope then? And if I want to know what is the value of a parameter, then I would do a confidence interval. So in this case, we're going to do a 90% confidence interval for the slope. And the formula for that looks like this. We're going to have B plus and minus T star times SEB. So B is that coef value, that 0.7033, plus and minus, and I need my T star. So my T star is based on degrees of freedom, which was 27, and it's also based on my confidence level of 90. So if I come in here to 27 degrees of freedom and 90% confident, then my T star is going to be 1.703. So let's write that down, 1.703 for my T star. Now I can plug that into my equation up here, so 1.703 times the standard error, which is 0.1015. So now I can do that calculation so I can get my margin of error of 1.703 times 0.1015, which is 0.1729. So 0.1729. So I'm just going to add and subtract that. So I get 0.7033 minus 0.1729, which is 0.5304. And then I'm going to have 0.7033 plus 0.1729, which I get 0.8762. So that would be my confidence interval. So we're 90% confident that the slope of the true regression between height and arm span, like if we had everybody, not just these 29 students, would be between 0.53 and 0.87, somewhere in that interval. Okay, so once we've all done the fun stuff, whoops, one more. With the model, we can also do inference on prediction. So there's two types of inference we can do on prediction. We can do inference for individuals, and we can do inference for means. So here's my two questions here. Suppose your friend Jane has an arm span of 65 inches. What would be the 95% interval to predict Jane's height? And the other question says, suppose you're interested in determining the mean height for everyone who has an arm span of 65 inches. What would be a 95% interval for this prediction? So in Minitab, you could get the confidence interval and prediction interval. For an individual, then we use the prediction interval, and for a mean, we use the confidence interval. So this first question, when we're talking about Jane, Jane's an individual, so we would use the PI, which is 61.730 to 70.725. And this one here, the second one, we want to know the mean height for everyone who has an arm span of 65 inches. So that one's going to be a CI, the confidence interval. So that's going to go from 65.404 to 67.052. So, and like really, the question on the test is just this easy. If you can identify, you know, prediction interval goes with an individual, confidence interval goes with the mean response, then you're going to have no problem figuring that one out on the exam. And one way to figure out that you're dealing with prediction in the first place is that you're given an X value. So it tells us in the problem, hey, X is 65. And then it starts talking about predictions. So that's when you kind of clue in, you're like, oh, okay, I'm going to use one of those intervals for prediction, either the CI or the PI. All right, next, talk about whether or not we meet the conditions for doing regression in the first place and whether or not our conclusions are valid, whether or not they meet the conditions. So there's basically 3 different graphs that we look at to help us figure out if we're meeting the conditions. We can look at the scatter plot that we created initially, the XY scatter plot. We're also going to look at a histogram of the residuals and a plot of the X variable versus the residuals. So our first condition is that the true relationship is linear. We would check that with the original scatter plot. So remember, that was the original XY scatter plot, and we did decide that, yeah, we do have a linear relationship. The other thing that we check it on is this residual plot of X versus the residuals. And what we're looking for here is trying to make sure that there's no rainbows or smiley faces. Those would both be red flags that indicated that the relationship was not linear. But if we look at the one for this example here, it looks good. There's no rainbows, there's no smileys. So it looks like, indeed, the relationship between arm span and height is linear. Next condition is that the response varies normally around the line. We check that one by doing a histogram of the residuals, and we want the histogram to be normal-ish. So this one, obviously not a perfect normal distribution, but it is roughly symmetric, a little bit more peaked in the middle, so this one is good enough. What would be a red flag is if it's like pretty skewed or skewed with strong outliers, something like that, that would cause us to be like, yeah, I don't know if this is right. But this one looks okay. The next one, that the observations are independent, can actually not be checked by looking at any graphs. Instead, we read the problem and we see how they collected their data. So in this case, the observations were made on college students. And so we kind of ask, okay, well, would George's height and arm span, would that affect Sally's height and arm span in our class? And no, right? Your height and arm span are not going to affect anybody else. So that makes you independent of your classmates or the classmates that were in this study. So we do have independent observations. So really, we're just looking here to see if there's repeat measurements on the same individual. And then finally, we want the standard deviation of the response to be the same for all values of X. So for that one, we're going to look at this residual plot here. And the red flag for this one is the megaphone shape in the residuals. So looking at our plot here, I don't see that. I don't see any problem with a megaphone shape or anything. So we don't have any of those red flags, which means that we meet that condition. So we've met all 4 of our conditions. So we're good to go ahead and do the analysis and draw and make conclusions based on our analysis because we do satisfy the conditions. All right, anybody have any questions in particular about regression or anything before we move on? Okay, and don't forget, at any time if you have a question, feel free to just turn your mic on and speak up, or you can type something in the chat window, and I can be happy to answer any of those questions. Okay, so the last new topic that we talked about was analysis of variance. So here's the scenario we're going to look at here. Is there a significant difference in gas prices from state to state? A group of statistics students decided to find out. They used yellowpages.com to find all the Shell gas stations in the city that they lived, and then they used random.org to randomly select 10 gas stations. They then looked up the gas price for each station using GasBuddy. All prices were measured on the same day, and here are the summary statistics. So you can see that in this case, we are comparing 4 states, New Jersey, New Mexico, Ohio, and Texas. And we just want to see if there's a difference. So when we're talking about writing the hypotheses for ANOVA, then the null hypothesis is going to be that all the means are equal. And in this case, we have 4 groups we're comparing, so we have 4 means. So null hypothesis is going to be mu1 equals mu2 equals mu3 equals mu4. And alternative hypothesis is that at least one mean is different. So at least one mean is different. And unlike chapter 25 and 26, where we had all these 2-for-1, 3-for-1 specials going on. There's none of that in ANOVA. There's just one way to write the hypotheses. This is the way to write the hypotheses. So the only slight variation you could have is if you wanted to just write out the words, all the means are equal for the null hypothesis, that would technically be correct also. So this is how we're going to write our hypotheses. So next up, what are the numerator and denominator degrees of freedom for the F statistic? So this is basically the only calculation that I can ask you to do for this chapter, because most everything else we're going to just take straight from the Minitab output. But it's not too hard to calculate these degrees of freedom. For numerator degrees of freedom, we have I minus 1. Okay, I is the number of groups being compared. So in this case, we have 4 states or 4 groups that we're comparing. So numerator degrees of freedom is 4 minus 1 or 3. So we have 3 numerator degrees of freedom. Denominator degrees of freedom, we have capital N minus I. Capital N is the total number of observations in all the samples combined. So in this case, there was 10 in each of my states here, so I ended up with 40 total observations. So 40 is my capital N. And then I'm going to subtract off the number of groups that are being compared, which in this case was 4. So 40 minus 4 gives me 36 degrees of freedom. And just make sure when you're doing the second calculation that you're subtracting the number of groups and that you don't get sidetracked by that number you just calculated and subtract the 3 instead of the 4. So put that number in. So 36 degrees of freedom for the denominator. All right, so looking at the conditions for doing analysis of variance, we have first condition is that we have a simple random sample, and we would get that by reading the problem. And in this case, these students did write down every gas station, and then they used a random number generator to pick which gas stations were going to be a part of theirs. So it is a simple random sample from each of the cities that they looked at, not necessarily each of the states that they were from, but it was a simple random sample from those cities. And then we also want all the populations to be normally distributed. So we can check that by looking at histograms of each of our samples. And if those are fairly normalish, then we can feel like we meet this condition. So all of these, we don't have any outliers really. They're fairly symmetric-ish in shape. You know, like I said, not severe skewness or big outliers. So we'll feel pretty good about that one. And then the last one is that all populations have the same standard deviation. And we check that by making sure that the largest sample standard deviation is less than twice the smallest standard deviation. So I just looked down here at my means table. My largest S was 0.0807. And then my smallest S was 0.047. So if I do that little calculation there, so 0.047 times 2, I get 0.094. Okay, so once I've filled in all the values, done the calculation, then I look at this inequality and I just see if it's true. So I look at it, I say 0.0807, is that less than 0.094? The answer is yes. So it's true. That means that we do meet that condition, that requirement. All right, now that we've talked about conditions, we're ready to go ahead and do the actual analysis. So here's the Minitab output. Our test statistic here in the analysis of variance table is F, which in this case equals 44.44. And our p-value over here, essentially 0. And we know that when p is low, HO must go. So we would reject the null hypothesis and conclude that at least one mean is different. Well, which mean or means are different? We can kind of use here's box plots that kind of give us a nice visual. If we looked at those first, we would probably think there is definitely going to be some differences there. We can use our interval plot, either, this one was done on Minitab 14, so it's the ghetto version. Minitab 17 and 18, and I believe Minitab Express as well, do much prettier versions, but they all work essentially the same way. What we're looking for in these interval plots is how much overlap or not overlap there is between these confidence intervals. Remember, a confidence interval says, hey, we're pretty sure that the mean is in here. So if you're pretty sure it's in this interval and that interval doesn't overlap another interval, then that would mean you're pretty sure that those two are different. So looking here, you can see that New Jersey doesn't overlap anybody and it's high. So it looks like New Jersey has the highest gas prices out of those 4 that we looked at. Second here, we have Ohio. So Ohio looks like it's cheaper than New Jersey, but still more expensive than New Mexico and Texas. And if you look at New Mexico and Texas, they pretty much overlap quite a bit. So I'd say that we do not have evidence that they are different from each other. And they're both the cheapest ones. So basically you would just say, hey, these are the differences. New Jersey's the most, Ohio's second most expensive, Texas and New Mexico are the cheapest, and they're not very different. Don't appear to be different from each other, or at least we don't have evidence of a difference from each other. So the moral of the story is that you should move to either Texas or New Mexico, which, of course, that's like a no-brainer. You should choose Texas out of those two because, I mean, that's what they teach you here from like the time you're in elementary school, right? That Texas is the best state of all. I always thought those people in college, when I went to college and I met people from Texas, I thought they were so obnoxious because they were always like, yay, go Texas. They had like Texas flags hanging in their dorm room and everything. And I was just like, oh, they're so annoying. But then I moved to Texas and now I totally get it. So it's all good. All right, so I think that is the end of what I have here. So just in general, couple comments about the exam. So I don't think this test is as hard as either of the last two, so 3 or 4. I would say it's about the same difficulty as maybe test 2. I mean, it is tough because it's cumulative, but at the same time, the calculations aren't as hard. And I didn't try to find like obscure concepts or anything to test you on. But here's what I see happen with this test. So by this point in the semester, you can take a look at your grade and you can figure out exactly what you need to get on the final in order to get the grade that you're hoping for. So in order to get an A in the class or a B in the class or whatever. And so I have had people that do that and they're like, oh my gosh, I've got to get like a 90 on this test in order to get the A in the class that I want. And they study really hard and they get an A on the test and they get the grade that they want, and it's fantastic. So I do think it's very possible to study hard and be successful on this test. On the other end of the spectrum, I have had people that look at their grade and they're like, oh, well, I only need a 65 on this test in order to get an A in the class. So I'm not even going to study. I can just walk in there and take this and be fine. And I've seen those people tank on the final and not get a good final grade in the class because they blew off the final. So, so be very careful. If you feel like you have a lot of leeway for the final, that's fantastic, but still give it a good study. Because like I said, I've had more than one student that's come back super unhappy because they are not going to end up with the grade they want in the class because they didn't bother to study for the final. And on the other hand, like if you're still trying for that higher grade, the A or you're trying for, or maybe you're trying for the B, you're like right on the edge there. It's entirely possible. So study hard and you can definitely do it. So I think that's all I have to say. Does anybody have any questions or anything? Yeah.
So the materials like from the previous exam, I know there was like a lot of heavy calculations. So are we supposed to kind of know those calculations, or just a matter of recognizing, is this a sample Z or T or that?
Yeah, don't focus on the heavy calculations. Just, okay. Especially for that that matching scenario, you're just gonna have to be able to match those. In the other part, I would say look at, like I said, don't focus on the calculations from previous, focus on the concepts. So if you remember all the concepts, then you're pretty good. There is one calculation that's from previous, but I wouldn't spend so much time focusing on calculations just to get that one. I mean, that's 3 points. So hopefully you'll get it. If you go over the concepts, you'll figure out that calculation. And if you don't, then it's probably not worth all the extra time to study all the calculations for that one. Does that answer your question?
Oh, yes. Thank you.
Okay. Okay, so question on the chat says, do we come to class next Thursday? And so first of all, we don't have class on Thursday ever. But if you mean next Wednesday, then no. So once we've taken the final on Monday, then we are done. So I did invite my online students to come to this meeting too, and I can't tell based on some of the names just have numbers in them, so I'm not sure if anybody from my online section is here too. But for my in-class students, then either you can take the test in the testing center, or you can come to class and take it on Monday. Either way, taking to the testing center, you still have to complete it by Monday. And if you take it in class, then of course you'll complete it during class. And then after that, that's the end of statistics for you. And if you're one of my online students, then you have until next Thursday to complete the exam in your chosen testing center for that. So, but yeah, after the final, we're done. So good question, Ed. Anybody else? Okay, so I'm just gonna